Okay, so we're gonna stick 8-1 and 8-2 in the same day because I think they're pretty straightforward and easy. So solving the exponential equations and inequalities equations. Let's try exponential. Equations and inequalities. Okay, solving these guys. Here we go. We're going to do an example. Solve. And we're going to have, this is part A, 4 to the 2n minus 1 power equals 64. All right, so let's take a look at our bases. The bases are 4 and 64. The exponents are 2n minus 1 and 1. Our bases are not the same. However, there is a relationship between 64 and 4. 64 can be written as a power of 4. So 4 to the third power is 64. So let's substitute that in. So I've got 4 to the 2n minus 1 equals 4 to the third. Now our bases are exactly the same. And if this is going to be an equality like it says it is, the exponents need to be exactly the same. So set them equal to each other and solve for n so that you know you can decide what the exponent needs to be so that they're matching. So n, add 1. This is like a baby algebra 1 problem. You did this when you were a little kindergartner probably. N equals 2 when you solve for n. See, so easy. All right, let's do one as an inequality. So we'll solve 2 to the x plus 2 is greater than 1 over 32. Oh no, a fraction! Well, can't 1 over 32 be written as 32 to the negative first power? It means the same thing, right? And now it's going to be a whole lot like the first example. So look at our bases. We've got 2 and 32. 32 can be written as a power of 2. 32 is equal to 2 to the fifth power. So we can replace that 2 to the x plus 2 greater than 2 to the negative 5. Rules of exponents, right? 2 to the fifth, and then we've got this negative 1 here. So 2 to the fifth to the negative 1 is 2 to the negative fifth. Okay, so the bases are the same. Now let's just set our exponents. I say equal, but it's an inequality. Subtract 2, so x has to be greater than negative 7. Super easy, right? All right, so then let's take a look at the word problem real quick. I'd like you to open your textbooks to read the word problem. I'm not going to write it all out here. So open up to page 486. 486, and we're going to do the check your progress, the recycling problem. All right, and so this one's talking about aluminum cans, recycling aluminum cans. And we're going to use the general form y equals a times b to the x power. All right, and a is your y-intercept. Intercept, or initial condition if you want to think of it that way. Initial condition. X is time. Alrighty, and then y is the, I guess you could call it the output, for lack of a better word. All right, so let's take a look at the example, page 486. Check your progress, recycling. A manufacturer distributed 3.2 million aluminum cans in 2005. So that's your initial condition. You're starting out with A equals 3.2 million cans. In 2010, the manufacturer distributed 420,000 cans made from the recycled cans it had previously distributed. Assuming that the recycling rate continues, write an equation to model the distribution each year of cans that are made from recycled aluminum. So we don't have enough information yet because we want to do this at some arbitrary time, x, and we want to know how much, we want a y value of, that's our output of cans. All right, so we have y equals 3.2b to the x. Super not helpful for a model. We have 3 unknowns. It would be nice if we just had 2 unknowns, right? Our input and then our output. So let's look at what they give us. They say that in 2010, so time has gone by. You've gone from 2005 to 2010. So that's 5 years. That's our time. So in 5 years, the manufacturer distributed 420,000. That's an output. So over 5 years, 420,000. So 5 years, oh hey, that's a time, which is an x. So this is our x. Output is y. So we can go ahead and start building this. So y is 420,000 equals 3.2. Oh no, our units are all off. 420,000 versus 3.2 million. I think I'm going to be in millions. So 420,000, I'll write that in terms of millions. That's 0.42 million. So that's equal to 0.42 million. All right, just because I don't want to deal with all those zeros. All right, B. We don't know B. We don't know what our constant, our constant is, but X we know is 5 years. Okay, so let's solve for B. Divide by 3.2, divide by 3.2. And so we've got b to the 5th equals, you'll need your calculators for these, friends, because this is not the easiest thing in the world to do. 0.42 divided by 3.2 is 0.13125. And then to undo a 5th power, you'll have to do a 5th root, or a 1/5 power. So to the 1/5 power for me. So that's equal to 0.67, I'll round it. It's an ish, 0.67 is your B. So now we can plop it into our equation. Y equals 3.2 times B is 0.67x. So for any time x, you can find out your output. So then the part B is asking how many cans can be made. How many cans made from recycled aluminum can be expected in the year 2050? So we've got to figure out how much time has gone by. If we're starting in 2005, this is part B, 2005, and we're going to 2050, our time, or x, is equal to 45 years. So we can use our equation y equals 3.2 times 0.6 to the 45th power. So first order of operations, exponents first. So that means we're going to do that first. 0.67 to the 45th power, and then times 3.2. You've got a teeny tiny itty bitty little number, basically 0. So there's no more aluminum that can be recycled from the beginning 45 years later. I know, those were kind of tricky, but hang in there. I'll only give you a couple problems.